The industry is currently obsessed with deploying autonomous AI agents, equipping them with complex-sounding capabilities we call skills. There is a pervasive assumption that attaching these capabilities to a large language model automatically yields a more advanced, dependable system. In a standard deployment, a user interacts directly with a model, typing a prompt and waiting for a single response. Now, engineering teams are upgrading to agentic architectures to automate that back-and-forth process, only to find their production pipelines failing unpredictably. The root of this problem lies in conflating two completely different mechanisms: the execution of a task and the reliability of its result. AI skills are strictly an upgrade to the execution layer. They do absolutely nothing to improve the cognitive reasoning of the underlying model. We are going to deconstruct exactly why these automated workflows fail and detail how to engineer true reliability from the ground up. Because confusing workflow automation with system reliability is exactly what causes an AI product to break the moment it scales. Let's look at a typical data extraction skill embedded within a modern agent workflow. Once we strip away the polished user interface, we find there is no advanced reasoning engine hidden inside. The foundation of this skill is nothing more than a basic text prompt. It contains dynamic variables, so the agent can slot in new data on the fly. And finally, it is saved to a repository, so the system can trigger it repeatedly without human input. Think about the manual process of a user copying and pasting a prompt into an interface versus an agent triggering this saved configuration. The underlying API payload sent to the language model is entirely identical in both scenarios. Turning a prompt into a skill only removes the friction of running the task. The core logic, the system constraints, and the success criteria remain completely unchanged. A probabilistically weak prompt uses vague instructions, relying on the model to guess the correct context and leaving wide margins for hallucination. Taking a weak prompt and wrapping it in an automated execution layer instantly amplifies its potential for failure. The system will now execute this vulnerable instruction set thousands of times a second, completely stripped of human oversight. If the model hallucinates a single value, that error is immediately fed forward into downstream agent tasks, creating a cascading failure. In AI architectures, automation and accuracy are distinct metrics. High automation does not yield high accuracy. Applying a skill wrapper to a prompt simply scales the baseline reliability or unreliability of the initial logic. If deploying skills does not fix poor output quality, we have to look elsewhere for the source of consistency. True system reliability is intentionally architected at the structural level. Depending on a skill wrapper to correct bad outputs is an architectural vulnerability. You must design reliability into the system before introducing a single automated step. We replace the basic skill wrapper with a more rigorous framework, a reliability architecture. The foundation of this new architecture is rigorous input design. For a production agent, injecting explicit ground truth context alongside the core prompt is non-negotiable. This contextual injection physically narrows the probabilistic space that the language model operates within, reducing the paths it can take to an incorrect answer. You must define the exact parameters of the task, methodically stripping away all ambiguity from the instructions. This engineered input stands in stark contrast to the vague, zero-shot prompts that are often hidden inside off-the-shelf skills. By explicitly defining the task, you prevent the model from improvising outside of its intended scope. Engineering the input in this way mathematically limits the odds of failure before the model even begins its processing cycle. Once the input is engineered, we must secure the boundaries of the system environment itself. This requires setting clear, programmatic constraints on how the model is allowed to behave. We establish strict formatting locks to guarantee that the resulting output can be parsed by downstream software. We also define forbidden actions, explicitly instructing the model on what it is not allowed to generate. The final layer of this architecture is the establishment of explicit success criteria. The system must programmatically evaluate every single output against these metrics before it is allowed to trigger the next automated step. Think of this evaluation layer as a physical gate. It traps hallucinations and logical errors before they can spread through the network. By locking the prompt inside rigid constraints, A reliable environment forces every output to prove its accuracy before the system proceeds. With a robust architectural foundation in place, we can reevaluate the actual purpose of an AI skill. The execution speed that a skill provides is highly valuable, but only when it wraps a system that is already reliable. This heavily engineered node, complete with explicit inputs, constraints, and success criteria, is what you actually deploy into an automated workflow. A prompt never becomes more reliable simply because you converted it into a skill. The skill merely ensures that the task is faster, cleaner, and easier to execute. The rule for production pipelines is strict. You must optimize your inputs, precisely define the task, and lock down your constraints first. Only after the cognitive output is deterministic should you introduce execution wrappers to scale the process. Reliability is designed. Automation just scales it.